Go
Okay.
ahead, Swati. Yeah.
Yeah. So I didn't get time to think of something related to quadrilaterals or something that specific. And given that we know what all you usually do, like the job is not to teach children, but to, give them that little help without which they can't progress any further, and then let them struggle with it further, right? And figure it out. That's the whole idea, right? So what I was thinking, what would help you do your job better? So one very important thing in math pedagogy is learning trajectory, like how things should be sequenced, etc. Now, in order to understand that, or rather, in order to get that, what is very critical is understanding if, say, somebody is dealing with a particular theorem, okay, then what all is needed to prove that theorem, okay? And I'm not, by theorem, I'm not meaning just for geometry. It can be a number related theorem also, okay? So whenever you want to prove a mathematical result, which other results or which axioms lead up to that, okay? And if you are clear on this, then you know exactly how much to help a child, okay? So, and obviously you can't learn this at one go, but what we can do is we can get you started, okay? So that is one thing. And I thought one of the homeworks that I will give you today is to come up with this learning trajectory, or there is something else called, which is called a concept map. So what a concept map does is it connects the concepts in a hierarchical fashion, meaning how do you move from one concept to the next? So the first concept is needed to understand the second concept. Simple example, when you are teaching multiplication, okay, to make sense of what multiplication is, a child needs to know what addition is. When you are going to teach the, how to multiply bigger numbers, multi-digit numbers, a child needs to know place value, right? So the concept of place value, or the base 10 system, the concept of addition, these are very critical to understand the concept of multiplication. Now, so, that's how, you need to create a concept map. And it is a good idea to focus on the hierarchy of concepts, their interdependence, and all those things, and kind of remove it from the pedagogy, okay? Initially, I had found it difficult as a journey to separate it from the pedagogy, but later I realized its advantage, okay? See, pedagogically, you can do many things, okay? And it's okay if you, if children run into it and they ask questions, they bring it up themselves, there is no problem. But especially when you are developing a curriculum, you are sequencing not just lesson plan, but you are, basically sequencing how a child needs to progress, writing a textbook, figuring out syllabus, etc. Then it really makes sense to have that conceptual map and not always connected to pedagogy. Okay. So what I would like to do is, now mathematics in particular has a difficult situation because it is the form of understanding that starts at class 1 or even earlier, even at the pre-primary level. And we don't call it by some other name. See, science doesn't start as science in class 3 or at primary. It is called EVS, and it's not just science, but social science, science, etc. mixed up. So, EVS has a lot more flexibility. It is not so tight that you have to do these things. You have to develop certain attitude, skills, etc. in children, because it's not science. It's not a form of understanding. Whereas, okay, now only I'm getting Arun's mail, which says, shall we discuss graph? Okay, we can do that. But since I have already started talking about this, let me at least complete my, and then we can go on to graphs. But math as a form of understanding is there. We don't call it counting. We don't call it computation or anything. It is mathematics. So you need to do justice to that. So let me share few slides. These are all borrowed wisdom or whatever, okay, not my original thoughts, but these are very important ones, okay? And since you have the job of, not a typical teacher, most of you, something else, I think this is something that may be useful. So there are two main considerations when it comes to teaching math. One is called the epistemic consideration, basically the, nature of math as form of understanding and how it should influence the pedagogy of the subject. Okay. Now, math is different from science in several ways. In science, you independently experiment and verify if that result holds or not, right? And there is falsifiability and all those things. But in math, no matter how much experiment you do, that's usually never enough. That can give you a sense, absolutely. And you should do that, absolutely. But ultimately, you need to establish it on the basis of logic. That's the proof part. And usually, on one side, school mathematics is kind of very rule-driven. There's very little scope for play, or there was very little scope for play. But, and the way proofs are done is like, somebody else had proved it maybe hundreds of years ago or whatever, and we just read it, mug it up, etc. So very rarely is there an opportunity for a child to prove something on his or her own, okay? And if you haven't, then I will strongly recommend that you read at least the first couple of pages of A Mathematician's Lament, or what is it popularly known as Lockhart Lament. Okay, I'll put it in the chat. And he talks about, just search and you will get it on the net. It's a PDF. If you read the whole thing, awesome. If you don't, then at least read the first couple of 2-3 pages where he describes two nightmares. Okay, and I think many of us can relate to that. Okay. So most students usually don't get a test of mathematics, and that's exactly what you are trying to provide. It demands a disciplinary approach that includes not the content, but also methods of knowledge creation. Okay. This whole justification, why is this true? How can you show that? Okay. So, and math, because of its nature, it can be done to a very, very large extent. Okay. So that's where, since the possibility is there, why not try it? The second part, which is more important for primary, less and less as we move up, is the psychological consideration, like how a child learns and how that changes with the age of the child, etc. Now, sometimes because math starts so early, this epistemic consideration and psychological consideration clash with each other. And when that happens, psychological consideration must take priority, because ultimately the learner has to learn. And if the learner is not ready, or the learner needs in a certain phase of his or her life, that needs to be, acknowledged. At the same time,
Swati, I think it will be good to just sort of walk through it through examples, or ask people to give examples, so we are sure people have understood what this means.
okay.
Ask people, because you already gave an example of multiplication, digit multiplication, so on. Let's see what people understood, right? If they can give an example of it.
So, yeah, so I'll come to the example. Okay. After to children, how do you explain it to them? Okay. How do you explain it in a simple way that they can understand? For example, when you are teaching geometry to younger children, do you start with 3D shapes or 2D shapes, and why? This is a question for you.
I would start with 3D shape, then only they can touch and feel the object.
Okay, so why 3D shapes?
Then
Touch
they
and feel.
yeah.
Okay. Now, obviously, a very critical thing is understanding the difference between curved surfaces and plane surfaces, right? Because you can't teach them everything, right? But you need to get them familiar with, say, very basic shapes, 3D shapes, like the cuboid, cylinder, sphere, and let's say cone. Okay. How do you distinguish among these?
I think I would start with 2D shapes.
Okay, why would you start with 2D shapes?
It's not as complex as 3D because there are like 3 different dimensions there.
True, and that is how geometry goes. Okay, but if you think of a very young child, then the world is 3-dimensional, right?
Yeah.
I mean, formally geometry goes point, line, 2D, 3D. That's how it goes formally. But if you think of it from a child's experience, from a child's perspective, the world is 3-dimensional. It's not 2D. I mean, in school, we make it completely 2D because everything, blackboard, notebook, textbook, screens, everything is 2D. But actually, we live in a 3D world. So this is one example of a clash. Okay. So in class 1 or pre-primary, when you start, you actually start with 3D, which can be held, touched, felt, rolled, slid along along a surface, etc.
Right. Yeah.
Okay. And you get to 2D from 3D by you keep a ball, trace it out to get a circle. Or you keep a box, trace it out to get a rectangle. Okay. So you go from 3D to 2D.
So the 3D would be the psychological consideration in terms of what the child needs or what he can access. And the epistemic is sort of what Ganesh brought up, saying it's simpler in terms of
Yes.
principles of understanding it.
Yes. Yes. Now, the exciting part, the part where we can bring in a lot of creativity, and people have been doing it, and trust me, it is fun, is whenever there is this clash, how can we minimize the epistemic gap so that later on it doesn't create problem? Okay. One of the classic example is, I may have shared it earlier. Usually a child in class 1 or 2 is told, you cannot subtract 9 from 3. You cannot. And the child kind of accepts it, yeah. But the moment this same child reaches class 6, you can. And you have a definite answer. Right? So how come the can't became possible in few years? So obviously you need to have a sense of negative numbers if you want to subtract 9 from 3. And it is a very, very abstract notion, this whole sense of negative numbers, etc. So you cannot tell that to a child you cannot introduce negative integers in class 1 or 2. Unless, of course, the child asks some questions based on observation of life situations, etc. And then you can try to, give him or her some sense. I know of at least 2 children who have asked. One was 5 and another picked it up because she observed purchase situation where somebody was purchasing an item which was, there was this, and she was puzzled because whatever math she knew, I believe she was in class 1 or 2 at this time when she observed this. She was very confused, how is the math working out? Okay. So that can happen. And then you absolutely need to explain it to the best possibility. And it can be a great opportunity to stretch their imagination, etc. Okay. But unless the situation presents itself, you can't introduce, maybe it is too early. At the same time, you can't say it is not possible. That's too strong a statement and in fact incorrect. You can subtract 9 from 3, but the kind of number you will get, you are not familiar with that kind of number yet. So you have to wait a bit. Okay. That's one. Another would be this associative and distributive laws, associative property of multiplication, distributive law. These are actually used, though we may not be very aware of them. Now, do you just tell them to children that this works? Usually that is how textbooks deal with them. They are just told, at the most what happens is you will do examples. So let me get to another PPT. Okay. Because this I can illustrate well. Okay. So Okay, so typically if you want to check associativity of multiplication, you take examples. You try, let's say, you compute whatever is this, then you compute this, and then you conclude that they are equal. Okay. Okay. And then you do several such. Now, when you do that, you can do that. That is verification. That's not enough. Okay. What other option is there? You have to basically create a model which generalizes this and which will work for any three natural numbers. Okay. And let me share that. It comes from the pullout. Okay. So okay. So you see these are plates with some blocks. Each block has a certain number of squares. Okay. So we have 7 plates and 3 blocks in each plate and 4 squares in each block. Okay. Now we want to count how many squares are there altogether. And there are 2 ways of doing it. Okay. So that's the main question. How many squares in altogether? So one way will be how many squares in each plate, and we find that. Then you can say, okay, so how many squares in all plates together? So that's that, right? Another way of doing it would be, so that's how you get the first one. Okay. Another option would be how many blocks in all plates. Okay. And you find that. And then how many squares in all plates. Okay. And you are counting the same thing, but you are counting them in 2 different ways, right? So these 2 numbers must be the same. Okay. Now notice the number of plate can be any natural number. Okay. Now if it is 0, then the whole thing gets proved even simply, right? Once you have established 0 times anything is 0, and so anything times 0 is 0, right? Similarly, you can change the number of blocks per plate to any natural number. Again, you can deal with 0 also, right? And third, you can change how many squares per block. Now, if you want to demonstrate this practically, you can have bundles of toothpicks or twigs or something instead of squares and blocks. Okay. And of course, you can get plates or bowls. Okay. Now, when you do that, then you see it's not a case-by-case verification, but one model or one way that can help you figure it out for any natural numbers. Yes. If you have like a block of like 10 lakh squares, you can't draw it. You have to imagine it. If you want to imagine, let's say 1 crore blocks per plate, obviously you can't produce it physically. You have to imagine it. Or if you want to imagine 2 billion plates, right? You have to stretch your imagination, absolutely. But it still holds. The logic, the argument still holds, right? So you can see that this is more generalizable than the case by case. Did you see that? The case-by-case verification versus where you generalize it for all possible natural numbers in through one model. Okay. So this model is minimizing that epistemic gap. When you do case-by-case verification, you are doing science, not math. When you provide them with such a general thing that works for all natural numbers, then you are doing math. Okay. Now, homework 1, can somebody please note this? I'll try to put it in chat. Oh, sorry. Homework 1. Okay, I just forgot what was homework 1. Hang on. Oh boy. Okay, I'll try to recollect. Too many things going on. Okay. Now, this is what happens as you go up, as the child grows up. Okay. Epistemic considerations increases and psychological ones decrease. Okay. So the older the child, you focus more on the math, nature of math, etc. And you know, the gap between the teacher and the student kind of decreases. Okay, because the student is already an adult and the child is getting closer to that. In some ways, it does become a bit easier in that sense. However, this is where a lot depends on experience. And upper primary, 6, 7, 8, or let's say 4, 5, 6, 7, 8 is an extremely gray area. So what kind of experience they have, a lot depends on that. By the time they are 9, 10, it's quite late to change their. Your last chance of getting them to be more why-based, getting them to not be satisfied with half-baked ideas and seek justification. Okay, so that is where it is very, very critical. And this in a sense how these two considerations impact pedagogy and assessment overall. Okay. So since you are recording, you can, you know, use screenshots, etc. Okay, now I have remembered the homework and I'm basically typing it out. See, there is commutativity and associativity of addition. There is commutativity and associativity of multiplication. Okay, and we are right now talking about whole numbers only. Okay. Now, where do we use it? Okay, in our regular calculation, etc. So that is the homework, to figure it out, find them out. Now, out of these, and then the fifth one is, okay, fifth one I'm going to ask now. Distributive property distributivity of multiplication over addition, that for natural numbers. Where do you think that gets used? And I'm asking you to look at standard algorithms and usually how we do calculation with natural numbers and whole numbers. Okay, since nobody has answered, so that becomes the fifth homework. Okay, so that's the homework for next week. There may be more, but definitely this much. Okay, and also, like I gave you an example of how we can show it, right? Show associativity of multiplication. Okay, and this is not the only way, by the way. There is another way also. Okay, so I want you to figure out, at least think, how to show these five how to justify these five. Or rather four, because one we have already shown. Okay, so think about that. Okay, okay, now you wanted to discuss graph. First of all, any question or any thoughts, anything?
So I think we have to show this with examples.
So you have to justify. So just showing one or two examples won't give you enough to justify. So how do you generalize? You can start with examples, absolutely. But then you have to come to a generalization.
Okay.
Okay, like this model of plates and blocks and squares, it can be generalized for any set of three natural numbers. Okay, so likewise, you have to come up with a model or something that can be generalized for all natural numbers. Okay. The advantage of natural numbers is, these are counting numbers. So you can think in terms of tables, bundles of sticks, draw them as circles, squares, whatever. There are so many different ways to model them, or even put it in a life, daily life context or something. They are the easiest ones. Okay, now graphs. What do you want to discuss regarding graphs? Now, do you mean graphs of functions like y equal to fx, those kind of things? Or do you, along with that, also mean statistical graphs? Histogram, line graph.
Statistical graphs.
Statistical graphs. Okay. So, okay. So which ones?
Bar graph, pie chart.
Okay. So what are the questions you have regarding pie chart?
Usually these graphs are introduced in 8th grade.
These graphs are?
Introduced in 8th grade for children.
Yeah. Pie chart does come in at 8th grade. Yeah. So what questions do you have regarding pie chart?
How do we introduce these graphs?
Ganesh, I couldn't hear you clearly. Sorry, Arun.
I mean, how to introduce these graphs?
How to introduce? Okay.
Can be
Okay.
introduced by after knowing the ratio.
Yes, Vasant.
For example, when the student in the 8th grade
So,
already know the ratio,
yeah.
we can now incorporate the pie chart with the ratio.
Yeah. See, basically, if you have shown children fractions using the Jodogan kit, okay, so they know fractions as parts of circles, as sectors of circles. That is a prerequisite for pie chart. Okay. Now, the thing is, why do we have already got bar charts, we have histograms. So how does pi help, or where is pi more appropriate than those other two? That's a very important question. Okay. Any thoughts?
From the whole, how much one is contributing?
Not the how much whole. Pi is not good in terms of absolute frequency. If a pi is not labeled at all, okay, and you just have sectors,
It should be with both angles and percentage, then it is better.
yeah, so let's say if I give you I don't know which is easier. I mean, I don't know how to directly include a pie chart in here, but we can do it in Excel, right? Yeah. So maybe I should share my screen for Excel. Okay, I'll just do that. Okay. Okay. Now, no, what I should do is create a pie, show it to you, because if I do it here, you will know what is the values. That's not going to help. Okay. So let me create a pie and then show it to you. Okay. Okay. So here, okay. Now you have a rough sense. What can you see? This is a pie chart. Okay, no label, nothing. You have different colors and you can, say in terms of colors.
Difficult to understand how much each.
True, you cannot understand how much. I completely agree. But what can you understand?
There are 4 different sectors.
You can easily compare the 4 things.
Compare for what?
Comparing the 4 quantities, 4 colors.
Okay, and how do you compare?
Visually, you can look at the sides.
Sector angles.
Can you figure out which one, like ABCD, which one has smallest frequency?
D.
Okay. Can you figure out, can you order them in terms of going from the smallest frequency to highest frequency?
D, C, A, B.
Okay. Can you figure out the total frequency or frequency of any of these?
No.
You can order the frequencies. That's good. So it's not that you don't know anything. You do. Okay. Can you estimate what is the size of A? Can you give some estimate?
No.
Okay. What would be your estimate for A?
I can only say it's like visually it's almost double, like half the size of C, but I cannot say how much.
Okay. 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 So you are giving it terms of, with respect to C. So you are looking at the ratio of the two, right? Now, do you also see that sometimes, from this graph, the frequency of one group seems to be equal to the frequency of 2 other groups?
Yes.
See, the largest, the modal group is B, right? The highest frequency. Is there 2 groups whose frequency together matches that of B?
D and A.
Yeah.
Exactly, D and A. Yeah. Can you give another such example?
C and D matches with A.
C, D, A.
Yes. So see, when it comes to this relative frequencies, when we talk about proportion, then we can extract a lot of things out of this. For example, can you say if the relative frequency of A is, can you put a percentage? So relative frequency is often expressed in terms of percentage. Can you estimate the relative frequency of A? mean, you don't have to be exact, but roughly what do you
Around
think will be the percentage?
30% or something.
Okay. And can you give any kind of justification towards that? Why you think it will be 30%?
Like if I consider this yellow part as like basic part,
Feel free to annotate.
I consider this part as basic part,
Okay.
then
Yeah.
this looks like double of that part. So there are 3 parts. Then it will be like
Okay.
this is addition of both parts. So it's total 6 parts, and this part will become so this is 3 plus this 1 plus this 3.
Uh-huh.
Then this part will become 4. So 4.
Yeah.
And this is 2. So
And you got it exactly. It was not an estimate. So see, a pie can help you in this way. Whenever you are interested more in the relative frequency, in the proportion, then pie chart is extremely helpful. Okay. And often we are in a situation where the absolute number is not important, but the, rather these percentages are more important. And that is where pie charts come in. For example, you will see when it comes to budget, okay, budget of the country, we usually have this percentage, these pie charts, and the way it is expressed is how much, what portion of 1 rupee is getting used for what. So the 1 rupee is the whole, okay, 100%. Okay, so if the total budget is the whole total budget is considered, mapped to 1 rupee. And so then the percentage is how many paisa out of that. Okay. I mean, since we have 100 paisa equal to 1 rupee, that kind of, and we're talking budget, that probably makes more sense than saying percentage. Okay. And since the goal of a budget, right, or rather the newspapers, when they publish this, the main idea is to communicate to the largest possible audience. Okay. They will use what works the best, right? So that's why they say it in terms of rupee and paisa. And you may notice this, at least I have noticed it. These pie charts are more common nowadays than they were when we were much younger. We were children. Okay. So this is what pie helps. Now, when we talk about statistics, there are mainly 2 kinds of, okay, let me. So there are mainly 2 types of data. Okay. And they impact what kind of graph you can have. Okay. So the first category is qualitative and the second category is quantitative. Okay. And each one has few other categories within it. But let's first talk about, okay, when we say qualitative, does it mean it can't have numbers? Let's say we have customer details. Okay. So we will have the age of the customer, the gender of the customer, possibly if the customer is married or not, depending upon what you are selling. You may want to know the education qualification of the customer. You most likely will have the phone number of the customer, maybe even address, which will include PIN code. Okay. So age of the customer, will that be qualitative or quantitative?
Quantitative.
Okay. So age comes here, right? Now, gender of the customer.
Quantitative.
Okay, you need to be clearer because is it qualitative or
Qualitative.
Qualitative.
okay? So that comes here. Okay. Phone number.
Quantitative.
Qualitative.
Okay, why qualitative or why quantitative?
It can be counted or measured as quantitative.
You need to speak louder, please.
Can be measured, counted.
Okay, and what are you measuring with phone number? See, if you are measuring something, then definitely it should be quantitative. Okay? Because the output of measurement is going to be a quantity, so definitely that kind of thing should be quantitative. Age, weight, height, etc. All of those are quantitative. Blood pressure, sugar level, okay? Marks you got in an exam or an interview. Time you took to run a particular distance. All these are quantitative things. Okay. How long you held your breath underwater. How much water you can drink in one go. These are all quantities. What does phone number measure?
Doesn't measure, but it's also not descriptive. Maybe it's not descriptive. I think it's not.
Okay, sorry, I didn't realize I had dropped out. So I think somebody said phone number, put phone number in quantitative bucket and said something about measurement. So if you measure anything, then that is definitely a quantity. Okay. So, and there are different things you can measure. Okay. How much water you can drink in one go, for example, many such things. So if you think that phone number is quantitative and because it is it measures something, what does it measure?
It's not measuring, but I think it's not also descriptive. Like it's not describing any quality of the.
Aha. Okay. What about PIN code?
Phone number can give the information about what kind of network they are using that number.
Yeah, I mean, I know people who can hear a number and immediately recognize whether it is BSNL or Vodafone or something else.
Nowadays, it's not the
So
case.
it does give you some sense, some description. You may not know the code to decode it.
Yeah,
For landlines, it's easier to decode.
Yeah.
There is an entry.
yeah, you may find the country, where they have. So we can get some information from that number.
The thing is, does it make sense to add two phone numbers or to add or subtract two phone numbers or add or subtract two pin codes?
No. No, but we can count the total, like number of phone numbers are there.
That's not what I'm talking about.
Okay.
We are not talking about number of phone numbers.
Mhm.
If you are looking at how many phone numbers a person has, that is definitely quantitative.
Mhm.
Absolutely, no doubt about it. Many people have two numbers, right?
Okay.
Many have three, many have one. There are few rare people who have zero, even today. Okay.
Yeah.
So that definitely is a quantity, but that's not what I'm talking about. We are talking about just phone number. See, things like phone number and pin code, these are like labels. And yes, if you know how they are coded, okay, pin code is easier. You can find it on the net. Like first students, the district, there is a code, okay. If you know the code, you will be able to extract information out of it. Okay, so even though that looks very qualitative, looks very quantitative, they actually come here. Okay, so phone number, then pin code, they come here. Okay, now within qualitative, there are two categories which are, one is the category that cannot be ordered at all. Okay, so that is called categorical. Okay, no natural order. So you can say, if you are looking for your favorite cricketer, okay, yes, you as a fan can decide whether Tendulkar was a better batsman than Gavaskar. Okay, or if Dhoni was a better captain than Kapil Dev. You can have your subjective opinions, but there is no natural order. Or if you think of favorite fruits, so these are categorical. And then there is another class called ordinal, where there is a natural category. If you have ever been to a dentist, then for a crown replacement, RCT, etc., they have a scale on the whiteness of your teeth, and they try to match that color when they have to make a new crown for you. Okay, now that is all colors, but there is an order, right, from darker to lighter. Remember, Fair and Lovely ads all colors, but there is a spectrum, darker to lighter. Okay, or shades. Or if you think of, let's say, educational qualification in terms of, never been to school, primary dropout, up to middle school, secondary, higher secondary, graduation, post-graduation, there is a clear order. Okay, the one which we are probably most familiar with is customer service response, service, right? Whether we liked their service, how much, and whether we disliked their service, how much. So usually it is put in a quantitative thing of a scale of 0 to 10, where 0 is hated it and 10 is loved it, right? But essentially that is also ordinal. It has been quantified, but those are ordinal, okay? Likes, dislikes, shades of whiteness or fairness, education level. So these are all ordinal data, okay, which has a natural order in them. Okay. Now, similarly, when it comes to quantitative, there are two kinds.
Swati, I have.
One is called, yeah.
So why the categorical is coming under only the qualitative? So why can't be coming under quantitative? Let us take that example you said. When you compare the two captain, I'm comparing with this statistical data, like how many matches or how much average they have. Then it should come under quantitative, not in qualitative, right?
Look, if you are comparing based on how many matches they are playing, right? That's the quantitative thing. But if you are comparing your favorite cricketers, then there are so many things.
Yeah, so I agree that. So why you are putting that categorical in qualitative? So it can be coming under quantitative.
No. Okay, maybe, okay, that may be a more complex example, but when you are thinking about just broad category, you're thinking orange, apples, bananas.
Way, a mathematical way.
Okay, but you are taking one particular aspect, sweetness of, then they do become quantitative. Looking more broadly.
Okay, yeah.
Okay, then it's a total category.
Then it should be it should not comes under any one category. So it should be a third type.
No. Category is more broad. Try to understand that. Okay, in category, you are not measuring or counting. You are more choosing. Okay, let me put it this way. Think gender, right?
Yes.
Can you say one is more than the other? Forget being politically correct or not.
No.
Can you order them?
I agree.
In Python sets, no, they don't have an order. Sets of.
If you look in terms of plain simple color, okay, red, green, blue, yellow, okay, primary colors, then it has to be, you have to consider it as categorical. If you want to get into a very scientific way of, wavelength frequency or something, you can make it ordinal. And if you go down to very specific exact wavelength, etc., then yes, wavelength is something you measure, that is quantitative. It does depend to an extent on context. But when you are comparing two people, okay, as two favorite actors, as favorite actors, favorite cricketers, favorite sportsman, favorite singer, then that is very, very much categorical. All the languages in the world, they have a ranking, and that is based on how many people speak that language. Obviously, I think Chinese or English, one of them is the top, probably Chinese is the top, followed by English. And interestingly, Bengali beats Hindi because of Bangladesh, largely because of Bangladesh. And that has changed. Now there you are actually measuring something. So when you are ordering the languages, you are not saying how much literature is there or anything else. You are doing it in a very, very quantitative way. But when you are trying to do a market survey to find out, favorite item or broad categories, or in many cases, those categories, for example, let's look at this customer thing. Okay. Which state they come from. Would that be categorical or ordinal or quantitative?
Can be categorical.
Yeah. Okay. See, even when you put age as infant, below teenager, if you put them in such broad buckets, that will become ordinal and that will not remain quantitative. Okay. So there are certain gray areas, absolutely agree. Okay. Okay. Now within quantitative, there are two broad categories. One is called discrete, which usually comes from counting. Okay. The other one is called continuous, which comes from measurement. So when it is counting, you cannot have fractional stuff. Okay. So there's a discreteness, there's a definite gap between, two successive possibilities. That's why discrete. But in case of continuous, the data can take any value anywhere within a certain range. So that is why continuous. Okay. So height, weight, etc., those will be continuous. Now, age is actually continuous. However, we don't specify down to the second. Okay. For all practical purpose, we discretize it and we just say how many years. So then we are, making it discrete. So, because age is a measure of time. So that way, by nature, it is continuous. The way we deal with it is discrete. Okay. So anyway, we are as usual over time. So what I would like you to do, you have got those homeworks. Now, I'll give you a small statistics related homework since you want to get into statistical graphs. So now that you know these four types of data, okay? Now the question is, which graphs can be used for which type of data? Okay. And of course, why? Okay. And so there are two types of homeworks now. One is based on the properties, and there also there are two parts: use and how to justify, and meaning that you need to generalize. And for there's the graph thing, like now that you know there are 4 types of data, what kind of graph will suit which kind? Okay. Now, from whatever statistics you have learned anywhere, if you have any other type of data, because sometimes there is something called binary data. It's when the data has 2 categories only, yes and no, or black and white, I mean, something like that. And that's quite important. So, that's usually categorical, a branch of categorical or a subset of categorical. If you want to bring in those kind of things, that is perfectly fine too. Okay. So see you all next week, and I'm guessing we will continue with statistical graphs. Right?
Yes, thank you.
And I would really appreciate if you can send in your questions. So last homework. What are your questions related to stat graphs? Okay. And I would really request one of you, see, these are all posted on chats. If you can just send an email with all these homeworks together, that will be very helpful for me. Okay.
Yeah.
Okay. See you next week.
Thank you, Swati.
Thank you, sir.
Bye.
Bye.
Thank you. Bye.
Ganesh, you can stop record.